A wind tunnel with 40-foot diameter fans. A flight simulator that's 8 stories high. A joyride that makes Big Ben look small. A machine that pulls super film 10 miles long on a 200-pound reel. A mower that can cut your lawn in seconds. And a 300,000-pound rock eater. Now, world's biggest machines on Modern Marvels. For the last 100 years, machines have flown us around the globe and propelled us into space. Today, engineers and scientists are creating new machines to take us farther, faster than ever before. And those machines need to be tested.
The 80 by 120 subsonic wind tunnel, biggest in the world. Test section, 80 feet wide, 120 feet high. Airflow drive system, 6 40-foot diameter fans. Location, NASA Ames Research Center, Mountain View, California. Current manager, United States Air Force.
There's a lot we don't understand about how aircraft operate. We try to push the edge of the envelope with every new development to get a little bit more performance or a little bit safer performance out of aircraft. Wind tunnels are a very big part of making that job happen, of making both air travel safe for us and for making aircraft of the future having even better performance than what we have today.
Usually, wind tunnels employ scale models of aircraft for testing. But this giant structure is bigger than an airplane hangar and tests full-scale models of almost every kind of aircraft.
In the 80 by 120-foot test section, we can fit a 737-sized aircraft, which is unique in the world. No other facility has that capability to test that size of aircraft in a wind tunnel.
The soul of this wind tunnel is the set of colossal fans that create the wind.
What is behind me is what's called the fan drive. Every wind tunnel has a drive section. Some have multiple layers of blades. This one has one layer of blades because it's a low-speed subsonic wind tunnel. Each one of these nacelles that you see, there's 6 of them, has a 22,500 horsepower electric motor. It's driving 15 blades that you can see. They're 40-foot diameter on the outside. And that's basically what provides the energy to move the air around the test section.
These drive systems were built in the 1940s for the 40 by 80-foot closed return wind tunnel, the biggest wind tunnel at that time. In the 1980s, the addition of an 80 by 120-foot wind tunnel, which utilizes the same fan system, ushered in a new era of scientific study.
We're now walking forward within fan motor 4 of the 6 fan motors that drive the air within the wind tunnel. We have a large nacelle that houses the electric motor that drives the fan. The aft portion of this nacelle, which is over 60 feet long, is nothing more than an aerodynamic fairing to be sure that the airflow that comes through this channel actually has superior flow quality as it exits the fan motor area. Each fan has 15 blades. Here we're looking at one of the blades installed within the hub system itself. At the root of the blade, we see the graphite windings that have been installed to be able to withstand the high loads experienced during operation. Underneath the graphite, in the area of the blade root, we have the hydralignum wood, which is 3 times denser than normal birch wood, and as such 3 times stronger. The lighter color wood is spruce.
It was the Wright brothers who pioneered the use of wind tunnels to study the essentials of flight.
They actually are credited with building the first wind tunnel. Very, very small in size, and yet it was able to analyze and be able to demonstrate the lift and drag that an airfoil surface would experience when exposed to free stream air.
European engineers grasped this new science and built 9 wind tunnels in 9 years, during the run-up to World War I. But the war changed the face of aviation forever. The air superiority of Germany's flying aces made evident the need for a better understanding of wind dynamics. In 1915, the United States established the National Advisory Committee for Aeronautics, or NACA. By the time World War II began, the NACA had built a wide range of wind tunnels, including the first high-pressure wind tunnel in the world. During the war, the NACA began work on the National Full-Scale Aeronautics Complex in California. In 1958, when the NACA transformed into what we know today as NASA, the complex became part of the NASA Ames Research Center.
The intake section behind me is about a football field in length, and its purpose is to bring air into the test section of the wind tunnel. This particular wind tunnel pulls air through this aperture and exhausts it out the other side of the wind tunnel.
At the mouth of the intake section, the structure is 13 stories high. But in the test section, its height is reduced to 8 stories in order to generate high wind speeds.
So the wind just outside the aperture would be moving about 20 miles an hour. But by necking down, much like a garden hose when you're turning the spray nozzle, by a 6-to-1 ratio, we get the air up over 100 miles an hour by the time it reaches the test section area.
The model support system secures the aircraft while measuring the test data.
It can measure lift, it can measure drag, it can measure forces at different angles of attack, it can measure forces at different yaw angles so that you know what the aerodynamic forces are on the aircraft as it's flying.
The model support system alters the angle of yaw and the angle of attack, the 2 critical aircraft attitudes for testing. Rotating the aircraft in a nose-up or nose-down direction changes the angle of attack, while rotating the aircraft's nose left or nose right changes the yaw angle.
I'm standing on a turntable, which is 60 feet in diameter, and allows us to rotate the models within the wind tunnel so that we can get them at different yaw angles.
Underneath the 60-foot diameter turntable is the balance room, where all the measurements are logged and analyzed.
The model support systems that measure the forces on the models are very large and intricate machines that can make very exact measurements. So it really is a compilation of a whole host of some of the largest and most exotic machines in the world.
A wind tunnel isn't the only huge machine used to refine and maximize aeronautic capability. Once an aircraft has gone through years of rigorous testing and thousands of visits to the wind tunnel, actually flying it becomes the challenge. To help a pilot realize the potential of the aircraft and perfect his or her own skills, a flight simulator aids in the task.
NASA Ames Vertical Motion Simulator. Biggest range of motion simulator in the world. Weight, 70 tons. Maximum acceleration in vertical axis, 22 feet per second per second. Cab size, 1- and 2-man simulation cockpits.
This incredible machine is housed in a 10-story building located half a mile from the 80 by 120 wind tunnel.
It's called the vertical motion simulator, but it actually moves in all directions. It's called vertical because that's where its most movement is. What makes this simulator different is that all of the motions are all independent. No matter how much you pitch, that doesn't take away then from how much you can roll, or how much you can yaw, or how much you can then move vertically or laterally or fore and aft.
This means that the cab, with a pilot inside, can move in every direction a real aircraft moves.
So now we're going to roll out of this slight turn, and here you can feel the accelerations from the wake vortex.
A gigantic machine and an essential tool for pilots. the VMS is a far cry from the first attempts at flight simulation. In the early 1900s, various contraptions were designed to mimic the forces a pilot would encounter while in a flying machine. By the 1930s, the Link Trainer prepared many a pilot on the ground for the air battles of World War II. Pilots sat in cockpit replicas with functional controls. Although they didn't replicate all airplane motions, the cockpit controls did trigger springs, pumps, and valves to create rudimentary motion. And as the war progressed, the flight simulator soared in importance. The result? Improved pilot skills and decreased aircraft accidents.
NASA Ames has had a long history of big simulators. It goes back basically to the late 40s. You learn from each one that you build.
Built in 1980, the vertical motion simulator incorporated all the movement the previous simulators lacked. And the mechanics of this giant machine are as complex as any aircraft.
We're on the carriage of the vertical motion simulator, and where we're standing right now is directly underneath the simulator cab itself. This carriage provides 5 of the 6 degrees of freedom that the simulator has. If this is an airplane, this is your roll, this is your pitch, this is your yaw, this is what we would refer to as lateral, and then longitudinal directions. This actuator, as well as this actuator back here, provide the roll and the pitch axes. And as you come around here, this actuator that is laying horizontally actually extends and retracts and causes this blue cone here to rotate about its vertical center line, and that gives you the yaw axis that you would have in your airplane. And then right here on the deck, these two surfaces actually slide with respect to one another back and forth, and that gives you the longitudinal direction. And then this whole carriage traverses back and forth across the beam, giving you the lateral direction. We're at the base of the vertical motion simulator. What you see here are the drive motors that power the vertical axis. They go through gearboxes, which then are attached to pinions that drive racks that are located on either side of pneumatic counterbalances, which we refer to as equilibrators. What these are essentially a cylinder within a cylinder. The outer cylinder travels up and down on the inner cylinder, and then these cylinders are pressurized with nitrogen to essentially counterbalance this system.
The NASA Ames Vertical Motion Simulator consists of 5 interchangeable simulation cabs. Each cab contains a cockpit and controls that duplicate aircraft in early design phases and aircraft already flying.
We're in a simulated front cockpit of the shuttle. It feels like the real vehicle, and it has a large range of motion, so you're not limited where you just get a kind of a hint. You get a much better sensation here than you would in other simulators. Here comes the gear. We're on the ground, pitching over to get the nose wheel down. The chute is out, and I'll get on the brakes.
Flight simulators are extremely important to aeronautics. Before a new vehicle gets built, you simulate it. Before we test new systems, we simulate them. They usually want to try them out first for both safety and performance reasons in the simulation before you actually put them into flight test.
Massive machines like the VMS and the full-scale wind tunnel help us reach great heights. But what if we're going in the other direction? Into the depths of the Earth. When the fan engines in the 80 by 120 wind tunnel run at full speed, they consume about 100 megawatts of electricity. That's enough to power more than 60,000 homes. world's biggest machines will return on Modern Marvels. Some of the world's biggest machines are hidden far below the Earth's surface, digging, tunneling, and boring their way through rock. These gigantic machines do the work that men have done for millennia. A mining machine known as the Continuous Miner is one of the biggest, and Joy Mining Machinery's 12HM36 is the biggest of its kind.
12HM36, Continuous Miner. Mining rate 40 tons per minute. Weight 300,000 pounds. Lifespan 3 to 4 million tons. Onboard motors 13. Speed 1 inch per second. Individual parts over 100,000.
Continuous miners are found in underground mines all over the globe. They churn through coal, salt, gypsum, or potash, to name but a few materials that lie in their path. And the way these beastly machines are engineered and manufactured is just as impressive as their operation.
This machine took about 5,000 engineering hours before it's released to production, and then production takes over and it goes to build from there.
The 12HM36 is a custom-made machine with specific design criteria.
This miner that you're looking at is kind of deceiving in its size on my computer screen. This machine is over 45 feet long, it's 15 feet wide, and 10 feet high. One of the design criteria when we were building this machine was brought onto us by our customer.
This giant machine had to be designed in pieces that fit through a 5-foot square shaft for assembly underground.
I need to ensure that when I start piecing this together that things do fit, things do work properly, so that I don't get calls from the machine shop or the assembly floor saying this doesn't work or this doesn't fit. No engineer likes that.
At the Joy Mining Machinery manufacturing plant in Franklin, Pennsylvania, giant machine tools form, cut, and measure the enormous individual parts that make up the 12HM36 Continuous Miner. And it all begins with a plate of steel.
This is really the beginning where all our parts that are cut out of steel plate or bar stock. It's all started right here.
There are 7 behemoth burning machines that torch cut each individual piece of steel. With the touch of a few buttons, the burning begins.
It's a lot like a bolt of lightning, except we're pushing it through an 1/8-inch hole. I'm told that the temperature of the sun's 11,000 degrees, but we're 4 times that down at the cut. So it's a hot cut. And that's the finished part.
Among the most critical units of the 12HM36 are the electrical box encasements.
Our machines will work underground all their life, and anytime you're digging underground, you have a chance of running into a methane gas pocket. Nothing will keep methane gas from penetrating an electrical box.
So to keep miners safe, these electrical boxes are machine tooled so perfectly, any ignition that might occur inside the box won't pass into the open air.
This is a box that just came off. There can be no scratches or imperfections. Anything that could be a flame path for burning methane gas can't pass between here and the cover.
In addition to visual inspections, another giant machine aids in the precision measuring of each piece of the puzzle.
The fact that this machine will measure with 0.2 of a thousandth of an inch is so important to us because a lot of our tolerances that we have to hold are only 1/1000th of an inch.
Before the final pieces of the machine are sent to the customer, each 12HM36 is assembled, tested, and then disassembled for transport.
The machine has to be broken down into a very small size. It has to fit into a 5-foot square hole. So we're taking a 300,000-pound machine and breaking it into about 30 large pieces to put into the mine.
The continuous miner is a machine on a grand scale compared to the backbreaking tools of the early mining industry. Throughout the long history of mining, machines and contraptions of various sizes have been devised to move earth. But it wasn't until the late 19th century that real changes began to occur, and mining could delve deeper under the surface. With steam power and metal digging tools, mining got faster and just a little easier. But the inherent dangers to hundreds of miners working hundreds of feet underground were still very real and often deadly. Mining now depends on machines like the continuous miner to do the work previously done by so many men. The rotating drumhead, peppered with carbide steel teeth, is the lethal force that disintegrates the earth.
The cutting drums on the machine are 15 feet wide and they are 5 feet in diameter. Each drum weighs about 5 tons.
The stuff of nightmares. This machine churns 900 feet below the surface and uses a conveyor system to move the displaced minerals to a hauler. All aspects of the continuous miner are monitored with real-time accuracy, inside the mine, up at the surface, and anywhere on the globe.
Being able to remotely operate or remotely diagnose from any location gives the operator in the mine the expertise of not only other people within his organization that are experts, but it opens them up to the JOY organization, where we have a complete series of global experts that understand this equipment in its finest detail. This particular screen shows 3 separate machines that we've logged into in a given mine operating. And you can see the top view and a side view. And when you're actually cutting and operating, you'll have the slider bar on the side that gives us the actual mining height of the particular equipment.
The massive continuous mining machine that revolutionized the industry will continue to get bigger.
It is evolving all the time with new components, new technology. It's like the rest of the world, technology is expanding every day, and to meet market demands, you have to expand right along with it.
These giant machines have proven their importance to industry in their subterranean world. But can a machine become the latest and greatest city landmark? The 12HM36 continuous miner weighs more than 100 compact passenger cars. World's biggest machines will return on Modern Marvels, here on the History Channel. The Eiffel Tower, the Empire State Building, Taipei 101. These structures are prominent landmarks that promote tourism and business and display a distinctive architectural panache. But cities that want new and distinct monuments must look outside the box for alternatives. Why not a machine? Like the giant machine in the heart of London.
I haven't been to London unless you go on the London Eye. And where else can you get the view of a London?
It stands almost 3 times the height of the Statue of Liberty. It's as familiar as it is extraordinary.
We weren't necessarily wanting the biggest, but it, you can't resist, can you?
British Airways London Eye. Biggest observation wheel in the world. Wheel diameter, 442.9 feet. Steel, 1,874 tons. Glass passenger capsules, 32. Maximum passengers per capsule, 25. Steel cable, 3.7 miles. Passengers more than 1,500 per day.
The Eye obviously resembles a traditional Ferris wheel, but technically the Eye is different in 3 ways. First, the capsules are enclosed. Second, they're positioned on the outside of the wheel. And third, the whole structure is supported by an A-frame from one side only. This giant wheel was originally designed and built for celebrations of the millennium. Since then, it's become London's most popular attraction.
We decided that it shouldn't be just a landmark that you look at, it should be something that people could participate in.
The 32 totally enclosed air-conditioned capsules are the most important elements to the success of the machine.
Putting the capsules on the outside was also because we wanted people to have an unimpeded view through 360 degrees. You know, the idea that you're feeling like you're on top of a mountain, but in the middle of the city. Traditional Ferris wheels, Ferris capsules would have been hanging, and so at the top they would basically be hanging between the structure, and your view is obviously impeded by the structure. Here, nothing gets in the way of the view.
The capsules are attached to the external circumference of the wheel instead of being suspended. This requires more mechanical stabilization and technical complexity. Each capsule has a track on which a mounting ring rotates at the exact same speed the wheel rotates. This ensures the capsule floor is always level and is so smooth that movement can't be felt.
That ability to keep the floor level, allow people to walk around, means you have to motorize the capsule.
The earliest reference to a rotating wheel used for the sole purpose of pleasure dates to the 17th century. It was a hand-crank device known as the ups and downs. But in 1893, George Washington Ferris, Jr. designed the first mechanical wheel for the Chicago World's Fair, and it was a big one. His massive machine stood 250 feet tall, weighed 2,200 tons, and was powered by two 1,000 horsepower steam engines. There were 36 gondolas, each the size of a school bus. This giant wheel was an instant hit and was soon nicknamed the Ferris wheel. The name stuck, and the big wheel has become a worldwide symbol of good times. But engineering the London Eye was much more demanding than any Ferris wheel. To build this machine, engineers had to literally reinvent the wheel itself.
It's a cliche to say nobody can reinvent anything, and the cliche is, can you reinvent a wheel? But this wheel is different to any other wheel, and everybody who worked on it knows that they did reinvent something.
It rotates continuously at a rate of 0.6 miles per hour. A complete revolution takes 30 minutes.
If you stopped and started the wheel all the time, the journey time would be quite prolonged. So it's a fundamental requirement of the concept that we have a continuous wheel rotating all the time, and that we can get people onto a capsule that's moving in front of them. That means that you've got to run at a speed which is safe, and that safety has to cope with a whole range of visitors, from young, agile people to people who are quite infirm. This isn't a white-knuckle ride.
Welcome back, ladies and gents. Just watch your step as you come off the capsule.
Designed by Marks Barfield Architects, the London Eye was built in only 16 months with the help of hundreds of people from 5 European countries. It's the only cantilevered structure of its kind in the world.
We wanted it to be light in feeling, even though it's massive in size. We very quickly came to the idea of having a triangular truss, because visually that makes it much lighter. Traditionally, Ferris wheels have had a square truss.
More like a bicycle wheel than a Ferris wheel, the Eye is comprised of 80 spokes, over 3 miles of steel cable, all connected to a central spindle. That spindle is integral to the wheel's operation.
It doesn't look that big from down here, but if you put it on its side, it's 25 meters. Well, in lay terms, that's 7 stories high. So it's a big piece of steel.
The wheel had to be constructed horizontally on site. Then it was hoisted into its vertical position, a groundbreaking feat for a machine this large. In just 3 days, the wheel went up and became the 4th tallest structure in London. The daily operation of the eye involves many complex systems and a dedicated work staff.
This is the London Eye control room. We have a ride operator who looks after the boarding process and also the guest safety while they're on the wheel. It's his sole responsibility, and he uses the systems here to monitor capsule performance and the safety of the guests. What we've got here is the capsule control system, which is monitoring the capsule performance. The standard heads-up screen is this one here, which gives you the location of each capsule. We can interrogate any capsule by clicking on it, and then we go into a more detailed look at what is happening within the capsule. So we can monitor the floor level, which are these indicators here. We monitor the power supply, which is this area here. We monitor the doors, which is this area here. The drive system, which is this area here, and the transmission and PLC status here in the middle.
4 sets of tires powered by a hydraulic system rotate the giant wheel. An amazingly simple mechanism for a structure so large.
Well, we're here beside one of the 4 wheel sets. We've got 4 tyres on each wheel set, giving 16 in total. The pressure we clamp onto the rim is only 5 tonnes between the wheel sets, and this is through normal operating when we have 16 wheels on.
On close inspection, a visitor might notice that this giant wheel isn't really round.
The rim itself, although looks circular from a long way away, is just a series of straight edges. And all those straights are 5 metres long with a weld at either end, and then another straight.
Easier to construct a series of straight edges. Their perfect alignment creates the illusion of a circle. Initially, the London Eye was to stand for only 5 years before being moved to another location.
It's a startling thing to say in the middle of an historical city like London that you're going to build the biggest wheel overlooking the House of Parliament. And that concept took a bit of swallowing by certain people because it's not something that had been done before. And that led to the sort of hedging of the bets that, well, we'll make it temporary because if it's not a success, we can take it down.
But it is a success and will continue to rotate for years to come, thanks to its brilliant design, reliable mechanics, and eye-popping views.
It's become a much loved object. It's become the biggest tourist attraction in London, and nobody would dream of taking it down there.
To make the impossible possible is what big machines do, even when it comes to mowing the grass. The largest number of passengers to ride the British Airways London Eye in one day was 22,000. World's biggest machines will return on Modern Marvels. Maybe you're in the elite class of big machine owners who have a ride-on mower. Or maybe you're just wondering, is this the world's biggest lawnmower? Or this? Or this? Not even close. When you have 1,000 acres of grass to mow and only 4 days to do it, you'll want something like this.
Claas Cougar 1400, world's largest mower. Mowing width 45 feet. Mowing units 5. Fuel capacity 250 gallons diesel. Engine Mercedes-Benz 438 horsepower. Mowing speed 10 to 13 miles per hour.
There are nearly 100 million head of cattle in the United States, and they all need to be fed. Nutrient-rich grass is the best way to maintain healthy livestock, but the grass must be harvested during a very narrow window.
Behind me is the Claas 1400C Cougar. It's the largest self-propelled mower in the world. Has the ability to mow over 40 acres per hour.
Besides that, it's got a great cab.
It's very roomy and it's a very smooth ride. The cab also pivots So it's got an air flotation system and it has an air ride seat. So you can operate this machine at full capacity, full speed, all day long and be very comfortable. We have a 3-dimensional steering wheel. We can pivot it from the bottom, from the middle, and telescopic. All of our operation is the tip of our fingers right here. We can move the machine forward. We can move the machine backward by moving the handle. It is very easy to operate this machine. We can raise our mowers just by tapping the mower for the function going up. We can lower all the mowers down sequentially with just a tap of a button. You'll see all 360 degrees around the machine, there is glass. So we can see our mowers and see our area. On each individual window, we also have a windshield wiper. So on the front window, we have a windshield wiper that rotates 360 degrees.
But what makes this machine so efficient is its mowing width of 45 feet.
The Cougar utilizes 5 mowing segments. These are mowers that are attached to different arms that attach it to the main machine. And these mowing segments are 9-foot, 10-inch cutter bars with a conditioner on each one.
The conditioner is located on the mower bar and is similar to a giant vegetable peeler. It's a set of metal prongs that spin behind the mowing knives and scuff the grass's waxy layer for faster and more uniform drying.
The Claas cutter bar comes with 7 discs on each one of our 5 cutter beds, 2 knives per disc. That knife spins at 194 miles per hour. So when the crop is cut, it goes through, follows the disc around to the conditioner.
The tire's great width actually lessens compaction in the field, which is good for the grass.
It's 70 inches tall by 34 inches wide. That's a huge tire for the mowing industry. And what this gains us is smoother ride in the field and gains us more capacity than a standard tractor tire would.
And for a machine so big, it maneuvers with surprising agility.
Each individual mower can float up and down and side to side, so it can contour even the steepest of terrain.
The driver can also dodge anything in the field that might obstruct one of the mowers.
We can individually, with a tap of a button, raise or lower each mower.
The Cougar cuts grass fast, but it can also move fast from one job to the next.
Another challenge, obviously, is such a big machine, 45 feet in the field harvesting. When you go to transport it, we need to get it as a narrow configuration as possible. And that's why you see a unique design of folding, utilizing the arms to get it into a width when we're down the road of just over 11 feet.
Like a gigantic transformer, the Cougar's cab rotates completely around, retracts its 15-foot cutter bars from both sides of the central cab area, and then powers down the road at 25 miles per hour with its Mercedes-Benz engine.
Good news is the wife asked for a Mercedes. Bad news is it's in my mower, you know.
Reality for the driver of the Claas Cougar may be 1,000 acres of cut grass. But other big machines immerse us deep under the sea in a simulated 3-dimensional reality. If the Cougar were to mow the grass at the legendary Pebble Beach golf course, it would take less than 3 hours. World's biggest machines will return on Modern Marvels, here on the History Channel. Think big. That's the motto of the biggest theatrical film machines on the market today. They've taken us into space, shown us adrenaline-packed adventure, and allowed us to explore the ocean floor, all from the comfort of a movie theater that literally envelops the viewer.
IMAX, established 1967. Film frame, 10 times bigger than standard 35mm. IMAX projector speed, 5.2 feet per second, over 3 miles of film per hour. Projector film platter, 450 pounds of film.
Over the 40 years of development of our IMAX technology, it boils down to one thing. The IMAX experience is massive.
The size of the most common theatrical film stock is 35 millimeters.
It's a much bigger image on the film. In fact, IMAX is 10 times the image size of a typical 35 millimeter motion picture film. It's huge. IMAX is made on 70 millimeter film, which is twice as wide, but it goes to the camera horizontally.
Traditionally, 70 millimeter film would run through the camera and projector vertically. But by turning the film to run horizontally, the 70 millimeter width becomes the height dimension. Now each frame is the size of a baseball card and allows for much greater resolution and clarity. In order to project this monster-sized film, IMAX created an entirely new kind of projection machine.
We're standing here in the IMAX projection booth, and this is the world's largest reel unit. We call it the QTRU. It both feeds the film to the projector and takes the film back up. The QTRU platter system can hold upwards of 450 pounds of film per platter, which is the equivalent of about 10 miles of film.
IMAX projectors are the most powerful in the world and have a unique way of producing crystal clear images.
The film is held very close to the lens against an aperture block of glass to ensure that there's no flutter in the film surface area. And this results in a rock-steady image on the screen that is perfectly in focus.
Adhering to the old adage, bigger is better, IMAX devised yet another set of machines to challenge its own. IMAX 3D.
As complicated as IMAX is, there's one other format that's even more so, and that's the IMAX 3D format. With IMAX 3D, you're running 2 rolls of 70 millimeter film through the camera simultaneously. Each roll of film is exposed behind its own lens, and the lenses are on the camera about 2.5 inches apart, the same distance as your eyes are apart.
Director Howard Hall does the majority of his work underwater, where things really get interesting.
The IMAX 3D camera weighs 350 pounds. That's out of the water. Most of the work I do is with the camera in an underwater housing. And in the underwater housing, ready to go in the water, it weighs just about 1,300 pounds. It's a massive system.
It takes 2 cameramen and a team of divers to safely operate the machine in the deep sea. Of course, a more sophisticated camera requires a more sophisticated projector to create the 3D effect.
We use polarized glasses. Polarized glasses combined with polarizers in front of the 2 projection lenses allow the left eye to see the left image and the right eye to see the right image.
Polarized glasses are precisely matched with the polarizing filters of the projector's twin lenses. While the lenses superimpose separate left and right eye views onto the screen, the glasses make sure that each eye sees the appropriate image, allowing the brain to create a single 3D image. All these machines require a new method to view an IMAX production. Some of the biggest theater screens in the world.
In IMAX, everything has to be massive. The screen, wall-to-wall, floor-to-ceiling, the projector, the film frame, the brightness, the resolution, everything's big.
From laptop computers to mini TVs and DVD players, media all around us are getting smaller and smaller. But IMAX defies that strategy by providing an experience made possible only through the use of some of the world's biggest machines.